Good afternoon, everyone, and thanks, Ustim, for the first part of the presentation. I'll continue from there. So today I'll be talking about the stochastic optimization and wind engineering application. So a brief outline would be a start with the introduction, and then we talk about the source of uncertainties in wind engineering, and then we talk about the method for optimization and uncertainty, and some results and conclusions. So when we talk about design of tall buildings, generally what happens is tall buildings are flexible and they capture a lot of wind. So wind is a basic design criteria, and a deterministic approach is generally adopted for the analysis and design of buildings. And however, there are a lot of uncertainties which comes into picture, and typically the wind itself is stochastic, and we model the wind as a combination of the mean wind as well as the fluctuating component, and the mean wind is generally constant, and it varies, I don't know, something like hours to days. However, the gust wind is what the fluctuating component is, and it changes within seconds to a few 10 seconds or something like that. And we define the mean profile by the log law. And the mean profile has two parameters. One is the mean profile at a reference height as well as the roughness height. And the roughness height determines what the shape of the wind profile looks like. And depending upon if your building is in the city or it's on this ocean, it changes. And of course, we have the turbulent fluctuations, which Ustim has already explained in detail. So for the parameters, we have the mean wind velocity at a reference height. For that, we use a variable distribution. And for the roughness height, a uniform distribution depending upon where the location is, we take it from the codes. Another uncertainty that comes from is the direction as well as the mean velocity. These are correlated. And for this correlated samples is given by a wind rose. So wind rose for a particular location gives how the wind velocity and the directions are correlated. And here we have the wind rose for the Basel location in Switzerland at a height of 80 meters for a duration of 10 years. And for this, we use a cupola-based multivariate distribution, and we use this surrogate to sample from. So from the data, we create this cupola, and we could get the samples, correlated samples of the direction as well as the wind velocity from this surrogate. All right. Okay, now our motivation is these kind of unique structures which are built, and these aerodynamic shape modifications are used to reduce the wind force which are acting on the structures. Right. So the optimization objective would be to minimize the base shear and the base moment, which are the forces acting at the base of the structure, for which the foundation needs to be designed. And it would, by reducing that, we could reduce the cost of the project, for example. Right? And we make the structure aesthetically pleasing, so it has this twisting and the tapering things. And we fix the height, which is something like 180 meters. And we fix the built-up area at the top so that a fixed, I don't know, area can be sold by the customer or something like that. And most importantly, it would be able to resist the wind loads. So we have our problem now defined, and this is how our design space looks like. And we have two design variables, which is the angle of rotation as well as the semi-axis of the ellipse. So we have the elliptical geometry of the building. And we parameterize the geometry like this. So we have the tapering and twisting capabilities. And once you define these two parameters, geometry can be created easily. and we put it on the CFD domain. This is how a CFD domain looks like, and we have the inlet here from where the wind fluctuation comes in. And we use a standard height and length for the domain as shown here. And we use a slip at the top and wall. And on the bottom and the structure, we use no slip condition. Right. So for each of these geometries, we used mesh refinement to get a body fitted mesh and then use our CFD to solve it. And then we come to the optimization algorithm. So we use a stochastic gradient descent for our optimization. And we use a simple Monte Carlo estimate for the quantity of interest as well as the gradients. And to get the sensitivity, since we only had two parameters, we could easily use a finite differencing for the sensitivities. And once we have the stochastic sensitivities, we use a simple gradient descent to reach to the next optimization step. Right. Another thing we use is an adaptive sampling. So to evaluate the gradient directions, we need to have a number of samples at each of the optimization step. And the sample size we control by constraining the variance of the sample gradient as here. So the idea is we start with less number of samples, and as we go along, as we reach the optima, we need to have more number of samples. So the algorithm is as shown here. So we, at each optimization step, we start with the sample size we set. And then we take the samples and we compute the gradients with the finite difference and the test for the variance of the gradients. And if the test is satisfied, we continue to the next step with the same number of samples. And if the test fails, we increase the sample size. And we use this new improved sample size for the next step. So this is how the adopted stochastic optimization workflow looks like. So we start with defining the objective function and the geometry. And so we have the initial design. So we deform the building geometry and put it in the computational domain and remesh. And for each of the samples, we perform the CFD runs. And we get the use a Monte Carlo way to get the statistics of QI and the gradient. And we give it to the optimizer and get the new design update, and we continue the process. And one of our test cases is a low Reynolds number. So it's a steady flow at Reynolds number 100. You can see the pressure and flow is steady. And for that, we have the optimization results for the mean of the base moment. And in principle, it goes down by around 18%, and it's in around 30 optimization steps. And also the twist has a nice flow, and the semi-axis is a bit oscillating. And this could be due to the complexity of the problem. And so this is what our initial design was. We started off with a circular geometry from the top, and we ended up at a very elliptical geometry. And this is an ongoing test case, which is the, sorry. Yeah, so we now have the high Reynolds number case. But here, for the optimization, for the simplicity, for the results, I didn't consider the wind rose, so it was only one directional wind. So, and it has a very smooth reduction from 3.3 to around 2.8 in 5 optimization steps. And you can see, so the wind is flowing from this direction, right? So The shape has changed, reduced in this direction as in the final design, and the twist haven't changed much. And we are now working on the optimization with windrows again, which is going to be a bit complicated. Okay, to conclude, we have an adaptive sampling strategy for stochastic optimization, and is applied for tall building design. And for the low Reynolds number, we have some results, and for high Reynolds number, we are still working on it. And the next steps would be to have the CVR, which is also an ongoing process, and we would like to have some kind of a multi-level approach for the future. And I would like to thank colleagues and EU for the funding.